covering a song there by, how do you pronounce his name? Matt Ratch? Matt Ratch or Matt Rack? Yeah, Matt Rack. But he's just this incredible guy that we played before doing the Beethoven covering Mozart piece of music sort of thing. Remember that piece? That's him. And he does this song as well, which is absolutely amazing. And I went and asked Jackson, I just said, when I was playing it, because I thought, oh, maybe I've got it all wrong. Maybe I just really love this music, but you know, it's really tasteless or something. And I said, is this guy any good? And Jackson just laughed at me and said, yeah, he's completely amazing. And then very modestly just said, oh, I sometimes cover one of his songs or something like that. And that was all he said. And it took me a long time to go and look it up. And then when I did, I went, boom, why don't you have a big sign on your head saying, I play this? So you did that when you were at high school, was that right?
Yeah, that was the last year of high school.
That was amazing. And it seems to me that essentially everyone on the course has something, and a lot of people have something good, and quite a few people have something fantastic. And all of those categories are good. The fact that you all have something is awesome. You know, that's actually unbelievable. It'll be the first assignment ever we've done that, where everyone's had something. So I'm very pleased about that, because often some people try and just fall short and end up with nothing. And here it looks like no matter what happens, you'll be handing in something and it'll be a solid body. So that just sounds fantastic. And what's that?
Unless everyone fails the acceptances.
Unless everyone, yeah, look, you're a negative man. You can just concentrate on the bad things. But, you know, even if you fail all the acceptance tests and you get an eclipse error with Eclipse trying to explain the eclipse error and your house burns down and your leg falls off and, you know, everything goes wrong, even if those things happen, you've written something that works, you've put a lot of effort into it, it's clever, Gary's happy, you've done some awesome stuff, you've fooled around, you've learned how to program Java, you've done OO, you've learned about design patterns, you've worked with a partner and not killed each other, which is, you know, these are incredible achievements. So, yeah.
And you'll be able to reflect on all the bad things that happened to you in your design journal.
And you'll be able to reflect on all the bad things that happened to you in your design journal. And that's the part we love reading. Oh, look, he's crying. Everyone gather around. I've got a crying student. No, it's not. It's not like that, actually. It's not like that. Your tutors are very proud of you and rejoice in the things you do. And we understand the hardships, and we are so happy when you overcome them. Or even just try and grapple with them and just do the best you can. Makes us very, very happy. Okay, now, here are some quick problems. Let's have a look at these. John Bentley, I talked about programming pearls a couple of times. Here's a chapter out of the book. He's made it all available. It's an awesome book. You really should read this book. What are we after? We're after algorithm design techniques. Oh, not PostScript. We'll try. All right. Here's the problem. He's got a problem he's going to solve in lots of different ways. The problem is he gives you a list of numbers, an array of numbers, a vector of numbers. He wants to find the longest run, so starting from some point inside that array, going on to some other point, then stopping, and summing up all the numbers in that run. He wants to find the subsequence which has the maximum sum. So if they're all positive numbers, then yeah, obviously it's the whole thing added together gives you the maximum. But if there are negative numbers, then maybe you want to cut it short or start a bit later or something like that. So given this sequence here, for example, what's the maximum sum you can get by just looking at a subsequence of that? And it turns out the maximum one you can get is adding up all these numbers here. Is that cool? That's the problem. How would you code it? So this is an algorithm design thing. Think of all the different ways you could use to code this problem. What's the first one we think of? Brute force. Okay, let's look at brute force. Here's one brute force algorithm. It's cubic. We've got a max so far. We loop from 0 to n. We loop from the number we just considered to n. So this is terrible variable names. Start position, end position. So we'll consider all end positions between the start and the finish. We've got a sum. We sum up from the start to the finish, all the values, and we compare it with max so far, and we keep updating max so far. Max so far, bizarrely enough, is initialized to 0. What if it's entirely filled with negative numbers? Oh, I guess an empty subsequence has size 0. Okay, so can everyone see this? The complexity of this is n cubed. This takes order n, this is order n, and then you sum up, and that's order n. So it's n cubed. All right, can we speed that up? Obvious speed ups.
Keep track of the sum.
Yeah, keep track of the sum. Because suppose I've just added up all the numbers between 3 and 70. The next time through the loop, I need to add up all the numbers between 3 and 71. This algorithm starts as, oh, okay, throws away the old one and adds up all the numbers from 3 to 71. But actually, all I need to do is just add the 71st element of the array. Yeah. That will make it, turn it from being cubic into quadratic. Yeah. There it is. Just add on that extra element each time as you go through the loop. As the sequence gets one longer each time, just add one more element into the sum. Remember the sum from the last pass through. That's order n squared. Okay, they're two brute forces, n squared. N squared might be good enough, especially if your array vector isn't going to be very long. But I wonder if we can be smarter. He's got some other speed ups that are sort of hacky. But let's move on. Divide and conquer. Can you think how you could use a divide and conquer strategy to solve this? Yes, Chris, you're nodding. Can you think of it? Or are you just still thinking of it now? Can someone think of how you can use divide? Remember what's divide and conquer? You split it into two, solve the two, and then combine somehow. And we're really interested in that. We want the combination cost to be low. And I did distance of points away from each other. Yeah. So you saw the combination of points when we quartered the space.
Yeah, so split it in two.
Split it in two. Split the vector in two.
Find the smallest.
We want them to be equal sized, or we're not going to get divide and conquer working properly. We'll just have a chip and conquer if we divide it into n minus 1 and 1. We really want n on 2 and n on 2. Yep.
Find the biggest sub thing.
Find the biggest in both of them.
Yeah, and if it's on the edges, then you have to check.
Not even if it's on the edges. Think about the joining is the delicate thing here. It's clear enough that doing the two, and notice we had an n squared algorithm, so it's ripe for divide and conquer, isn't it? We're thinking, oh, if I can get a linear joining cost, then I'm going to get an n log n algorithm. And lo and behold, he did get an n log n algorithm. So it's ripe for it. So yep, you've broken it into the two, so that's half the amount of work we've got to do because it's quartered each one. Check which one's bigger as a constant time. Yeah.
Then don't you have to...
Then you have to work out, just think about the joining case. Everyone think about it. What's the joining case? What case haven't we considered?
In the middle of where the join.
Yeah, where the longest sequence spans the gap. Now, it's not necessarily the case that it will be one of the two longest you've already found in other half. Yep. So the longest in one half, entirely contained in one half, might be 50. The longest entirely contained in the other half might be 50. And there might be two of length 30 right on the gap. So when you put together, it gives you a length 60. So you haven't necessarily found it. So find one half, find the other, and then find the longest that crosses over. And that's easy enough because you just count in on one and count in on the other. Yeah. Count in. You can even go the whole way in. Find out the point that gave you the biggest sum starting at the beginning. Find the cumulative sum the whole way through the vector. Find the biggest number of that. And that's your biggest for this half. Do it that way. It's the biggest for that half. Add them together. That's your linked in one. It's linear cost. You just have to scan through each sub-half once. So we've got a linear combined cost. We've got we're halving the size, so quartering the cost of the other two. So we're going to, woohoo, it's looking good. Here we are. Divide into two sub-programs. Recursively find the maximum in the sub-vectors. Find the maximum crossing sub-vector. Return the maximum of the two, and it's n log n. Okay, cool. Very, very beautiful. You should definitely read this whole book. It's such an awesome book. Second puzzle is a famous puzzle, the 15 puzzle, invented by Sam Lloyd, who I love completely. Like Ernest Dudney or whatever his name is. He's like the American equivalent, the guy that just invented fun puzzles for thinking about in the shower. And when you're dancing with someone and stuck on a train. Just a whole book of really fun puzzles. He was awesome. He did the one with the man on the horse that's upside down, and you have to put them together, and invented all sorts of puzzles. And he actually made a living out of inventing puzzles. Who would have ever thought of that? And he came up with the 15 puzzle. It's a famous one. You know the sliding blocks where there's a little hole missing? It's normally a 4x4 square, so it's 16 squares, but you've got one missing. And you can slide them around, and you have to rearrange them into order. What algorithmic technique are you likely to use to solve that problem? You've got to find a sequence of, does everyone know the problem? Have I specified the problem well enough? Wave at me if you haven't quite got the problem, because you might not have seen this puzzle before. Has everyone seen it? Do you know the puzzle? You there? Yeah, you do. You do too? Yes? So you've got to move these shapes around. You can only move them into the hole that's there. Every time you move, the hole moves. Essentially, you're moving the hole around the board. And you've got to end up with the numbers in order, 1 to 15 with the gap hole at the end. What's that?
Like the one with the pictures where you move the one, the blocks around, you have to create a picture. Yeah.
Oh yeah, a picture. Yeah, I'm such a mathematician. There doesn't have to be anything to do with numbers. It's like Sudoku. I don't even know why they've got 9 numbers on them. They should have 9, what are there 9 of? 9 flowers? Is there 9 special for something? There's not 9 of anything? The 9, weren't there 9 rings held by the son of men? Come on, yeah, sure. No, there's got to be 9 something, the 9 horsemen or something. So, okay, so yeah, it could be anything, it doesn't have to be numbers. Yeah, well done. So you move a picture around. I should have thought the 9 pictures, the 9 signs of the zodiac, the 9 points of the compass. That sort of thing. Okay. Yeah. Okay. What algorithmic technique would you use to solve this problem? You've got to write a program to solve the 15 puzzle. Now, those of you that already know it will know it already, so thanks for not calling it out, because I know some of you do know. But those that don't know, please think. You could use brute force. Notice there's this annoying problem with using brute force. It does have the potential to go on forever. So remember I said the important thing with brute force is do make sure you are careful in the way you systematically enumerate things. Make sure you don't overlook things. Perhaps I should have also said make sure also you don't double count things. You don't enter loops, so you want to have some sort of loop detection, which again is a cost. So it's sounding like a bit of a pain to do that. I don't know. What's some way you can avoid having loop detection and all the costs involved with it? You can avoid having loop detection if you're essentially not doing depth-first searches. Any form of breadth-first search, for example, will avoid a loop detection problem, because you'll hit the solution before you went, you know, all solutions of one length are found before you look at all candidate solutions of the next length and so on. So you never get to an infinite length solution because you stop as soon as you hit the real one. So what do you think? 15, what would you use? Backtrack. Why? That's right. Absolutely. Why? Divide and conquer? What do you reckon?
Well, you can't really divide it.
Divide and conquer is just no clear way of how the heck you do divide and conquer. It doesn't seem to divide into 2 equal sized subproblems, because you break it into half, one of them's got a hole and one doesn't even have a hole in it. I mean, there's a whole new problem, the completely filled in square problem. Yeah, that's a really hard problem. So, yeah, what about greedy method?
Not sure.
Can't think of a greedy heuristic. It doesn't have the smell of a greedy problem, but yeah, every move seems to affect all subsequent moves. Maybe there is a greedy way of solving it, but it doesn't spring to mind, so we knock those 2 out. Brute force looks like there's too much work. We haven't done a cost of the complexity. Just that loop detection was freaking me out a bit, but maybe as an exercise before we moved on, we should calculate the cost, just to make sure brute force won't solve it. But I have a funny feeling that if you think of all permutations of 15 squares on of 16 squares, I guess, on a 16-way board, you've got 16 factorial ways of arranging them. I vaguely remember not every state is reachable in that problem. I think there are 2 parodies of it, so it's 16 factorial divided by 2. It's an enormously big number. So knocked out brute force. So yeah, divide and conquer is the natural next choice. I mean, backtrack's the next choice. Now, how would you do the backtrack?
Well, I guess to get to that state, well, obviously there's not every state is available.
Yes.
So I guess you could sort of do a move and then see what's possible, and then sort of do it follow.
Yeah.
At least some moves will actually lead to that state.
How many moves are in front of you at every option?
You've only got 3, unless you go backwards.
Yeah, okay. So essentially, there are 4 moves into a hole. One of them you've presumably just come from, so you've only got 3. And if the hole's on a side, you've only got 3 moves in, so presumably you've only got 2. If the hole's in the corner, you've only got 1. Okay, so you've got a tree with branching factor of 3, 2, and 1. It's presumably a very deep tree, because there could be lots of moves. So you're going to backtrack. How would you know to give up, though, in the backtrack? That's the thing with the backtrack. You've got to know when to stop. What's your pruning function going to be? Just when you hit a state you've already seen?
Yeah, or Yeah, possibly. Or you sort of get to a point where you can't move that piece into another position. I'm not sure.
You get to a point where you can't move that piece because it would be hitting a state you've already seen. Yeah. Okay. Because you can always go back, of course. Yeah. So if we did a backtrack and our pruning function was we gave up when we reached the state we'd already reached, notice we're still going to have to reach as many configurations as there are possible configurations on the board. So it's a brute force essentially still. Do you know what I mean? You're only going to prune and cut when you reach a solution state. You're never actually going to prune on a problem state, on a partly constructed thing. So that still seems like a lot of work. But keep thinking about it, because I think the gem of the solution's in there. You've nearly got it. Yeah.
Are you looking for the shortest?
The shortest sequence of moves? Any sequence of moves, but shortest would be nice.
Okay, because humans solve it with like greedy.
Yeah, humans solve it with greedy. That's right. Essentially, like Monte Carlo. They're just trying to get one in, and then trying to get the next one in, and then trying to get the next one in, and then trying to get the next one in, and trying to get the next one in. And you could almost do random moves to get them in, I guess. Can you or not?
You get it into a sort of a sequence around.
You get it. Oh, so you're doing extra thinking. So that's not quite greedy. Oh no, well it sort of is greedy. Yeah. Yeah. I think it's right. When you do it, don't you try and get one, and then you try and get two, and then you try and get three, and try and get four? I mean, there's probably some amazing Zen-like kid that just looks at it and goes, and suddenly they're all in. No, they can't all be in. At most, you can get one in a position on any move, can't you? Oh no, you can push a whole row along. Yeah, but anyway, yeah, that's cheating, isn't it?
To mess up the order you've already got to.
Yeah.
One piece in somewhere. So.
Yes.
Usually recover that.
No. There's algorithm, like there's sequences of moves that will guarantee that the notes that you don't want to move won't move.
So there are sequences of move that leaves it uncubed, unrubixed. That there are sequences of move that you can guarantee leave certain squares at the end untouched. So essentially, you can solve it in a greedy fashion using those moves. Very clever, very clever. It wasn't apparent to me, but now you say it. That's really clever. So I've never tried writing code to solve it in a greedy way. It'd be interesting to see how that goes. I've always gone for another way of solving it. Possibly because I'm normally looking for a short sequence of moves. Yeah. Breadth first search is a good way of doing it. Again, it's fairly exhaustive, but you will guarantee to find the shortest sequence of moves. What's the smallest number of moves you're going to have to make in a breadth first search, though? One or none if it's already in shape. So how do we relate the smallest number of moves we're going to have to make with the starting configuration?
The smallest number of moves that you could possibly would be the Manhattan distance.
Every piece is Manhattan distance from its destination. So the Manhattan distance is how many if you're traveling around in Manhattan, which is laid out like a grid, the Manhattan distance isn't like diagonals, doesn't take hypotenuses into account. It just says how many rows you've got to move up and how many columns you've got to move across. So you could work out for each piece how many rows and columns it is from its final destination, sum that together for all pieces, and that's the minimum number of moves. Now, if you start off with all pieces in the wrong spot, then your Manhattan distance is probably going to be at least one. It will be at least one. It'll probably be several. Let's say I'm randomly picking up a 3 or 4 or something like that. So you've got 3 or 4 moves for 16 squares. So that's like 50 moves or something. Is that right? We're looking around 50 moves. So we're doing a breadth first search to depth 50 on a tree that branches with a factor of 4. That's sounding like still a lot of work.
You might have to do it over, because the Manhattan distance.
That's an underestimate. Yeah, that's an underestimate of it. Yeah, that's an optimistic estimate of how much work. Yeah.
You could have like, with your idea of the Manhattan distance where you're bound, when you make a move, there has to be an overall improvement in, say, the sum or some sort of relationship.
Yes. Look, this is the normal, this is the way that is generally used to solve this when it has to be solved by a computer. People use a branch and bound algorithm, so it's like a backtrack algorithm, but rather than doing a breadth first search and ruthlessly, it's like the maze problem. Rather than having to do that one, then that one, then that one, then that one, when we've got a good indication it's this one, every time they've got a state, they look at the 4 possible children they could generate by moving, and they look at how good those children are. And how good they are is often just measured by something as simple as how many are in the right spot now, how many are in the wrong spot. And you favour children where there are more in the right spot. Yeah? And you use that heuristic. So you pick each time to consider a formula which is essentially how many moves are available for the children. Now this is called LC search or A star. So you might want to look A star up if you want to know more about this awesome algorithm. Yep.
To a point though where you've got each piece in the right spot and one like completely off in another place.
Yes.
You can't possibly get it there without screwing everything up.
Yeah.
Yeah, but that's all right. You, at every point, you just consider the best child. So
All of the children at that point.
if all the children are crap, you still got to pick the best one. It's like an election. You know, it's not necessarily you've got an awesome option in front of you. You might have backed yourself into a corner. Yeah, yeah.
End up, yeah, in a corner where you have a hole with 4 pieces around you that are in the right spot.
Yeah, yeah, yeah. Yeah, so this A star or LC search that I'm talking about is not an algorithm whose behavior is completely known up front and predictable and so on. This is a heuristic. We come up with a rough measure of how good a solution is. It's just a guesstimate of how good the solution is. We're mainly trying to pick it to be something we can evaluate quickly because we're going to have to do it all the time. We do the LC search, and it turns out LC search tends to work really well on problems like this. So in practice, it just tends that that's not the case. But maybe if we change the rules of the 15 puzzle, we might find that LC search sucked a bit and we might have to use other heuristic techniques. With a heuristic technique, you never know. There are always these what ifs. If the cards are arranged exactly like this, or the squares are arranged exactly like this, oh, we're stuffed. You know, this is going to be a really slow solution. Yeah, 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 that's heuristics. We don't get hard guarantees. We don't get worst case guarantees. But in practice, I can tell you for the 15 problem, I coded the 15 up using this search. It's like 3 or 4 lines of code. It's the simplest thing in the world. And it solves it like bling, not 3 or 4, but, you know, order of that. Yeah. Yeah. Okay, now, we're nearly finished. We've essentially finished. But I did want to just briefly talk about, remember I showed you this music from Jackson? And I just wanted to talk about it very briefly. Because this is the topic of our next lecture. I would like you to look at this thing here at about 1:45. And we'll look at it for about 10 or 12 seconds. Now, I stopped that and tried to go through it almost frame by frame, but it's so overexposed you can't see his face. I can't see your face, but I'm trying to see what it is. But just from the whole body language, watching that, don't you just think, oh, yeah. I just got the sense that at that moment, you were having so much fun. You were just in the zone. I don't know if fun's even the way of explaining it. And I just think sometimes when I see birds flying and things, I think, or surfers on an incredible wave, you just think, oh, yes, yes. And just the whole thing is you're thinking, that is, you know, that is a feeling that I want to have. And watching this, although it sounds crazy, and this is something that will come up in the next lecture, it sounds crazy to say, but you guys are probably the only people in the world I could say this to and it would even make the slightest sense. That is how I feel when I'm programming. When it is working, when the ideas are coming and you just go, oh, yes. It is just like that thing there. So there you go. All right, so we'll be talking about that a little bit, as well as the new algorithm programming solving technique. Next lecture, see you then. Bye.